Okay, great. So it's really nice to have Eva Silverstein to tell us about multipoint correlators. Please go ahead.
Thank you, and thanks to the organizers for putting together this wonderful meeting. So I'm going to talk about this subject. First, a disclaimer: if you're at Cambridge and you saw this when I spoke about it there, this will be basically the same talk. So please don't feel you need to sit through it again. Although the discussion is always welcome. So this is based on a couple of papers I put out with George Panagopoulos on the shape of the wave function with a focus on its high point correlators, or equivalently the tail of the distribution, as well as a paper that's really ready to go on kind of a fun analog of DBI inflation, where instead of the square root branch cut, we have a logarithmic branch cut. And instead of a large color expansion, we have a large flavor expansion. And so that was kind of an offshoot of this, and I'll try and summarize that as well here. This is related to many other people's works. This is a small list. I recommend this talk by Spiros, who gave a different kind of overlapping but complementary perspective on this subject that I enjoy very much in listening to his contribution. So these days, this is what a collaboration meeting looks like. George, Alex, Deshawn, and some friends here as well that consult. So this is Zeta, and she'll play a starring role. I want to also thank some basically shadow collaborators, Merdad, Leonardo, and Matthias Aldariaga, who were involved in a lot of this, actually. Okay, so for us, this started from a kind of formal question that we'll resolve. And this is one that's been going on for some decades, actually, having to do with what is the behavior of large endpoint correlation functions in quantum field theory generally. And this has been asked and partially addressed, but not fully addressed in flat Minkowski space-time quantum field theory. So the first observation is that if you have a tree diagram, or a tree part of a diagram, by very simple combinatorics, you see that there are n factorial contributions of, say, a 1 to n process or subprocess. And that factorial enhancement then is something that suggests that the effect gets large, but depending not just on lambda, but on n times lambda, where n is the number of points in the process. Of course, the kinematics matters. This was first established in very special kinematics, which is basically at threshold or close to threshold, where the outgoing particles are close to being at rest. In that situation, cancellations are easy to avoid, and this factorial enhancement that would be suggested by the combinatorics, in fact, does govern the answer. So it's been an interesting question: what happens when this quantity becomes of order 1? And it's something, because of all these outgoers, it's a problem that naturally is addressed by semi-classical methods, but that is something that is still challenging, although there's been a good amount of progress over the years, including a more recent progress. This has become a thing again more recently, also in the context of large charge expansions, which is also related, I think, to the bootstrap theme of this workshop. And this is just a also probably incomplete list of recent papers on that. So what people are finding is that if you consider even a situation without a large color, there's a kind of emergent semi-classics, an emergent Tuft-like expansion. Actually, with Polchinski, we were interested in this in a particular example some years ago, where in one of these stringy brane constructions, one can observe that the system of two types of branes could have a higher dimensional one that had one or just a few of those, so small color number with a large excitation of charge, and still there was a dual large radius gravity description of it. And interestingly, just working in quantum field theory, people have come to find a emergent Tuft expansion just at the level of quantum field theory diagrams and semi-classics. So I'd recommend, we had a talk that's public by Ricardo Rattazzi at SITP at Stanford that you can view if you're interested in this. It was beautifully explained. But as you can imagine, it's challenging to nail this down when it becomes strongly coupled. And the fun thing about the situation that we all know well in inflation and close to the center
sorry,
is,
can I ask a quick question? So there is no issue of perturbative unitarity if you go to large enough n, because you're computing at very, very specific kinematics, right? So if you go a little bit away, you could save perturbative unitarity.
So I think that's, in the right direction of trying to constrain this effect, but it's not, it's not enough. In fact, some of the early literature achieved a resummation at a non-zero moment. It doesn't literally have to be on threshold. So it's not, it's not on the nose constrained by what you're saying, although it seems, it would seem surprising if this survived, but I don't think it's been proved one way or the other. What has been done, forgetting about the question of whether there's some dramatic enhancement, we'll see that there is in cosmology, that'll be the point, but in basically just to foreshadow, because this configuration of being at low spatial momentum is very natural in our context, as you all know. But for this, regardless of whether it persists, there's no really good reason to say that it does. People have proposed semi-classical configurations that they say that it does persist, but what people have done in this vein achieves a resummation of certain quantities, like correlation functions in a large charge sector, without, which control, this regime where this becomes large without it corresponding to this enhancement. But what I'm saying is interesting about it still is this effect, this emergent Tuft expansion. So I think this is really intriguing. Again, in this past, there was just some, particular example where we noticed that, but then I just thought, okay, it's probably a peculiarity of this example because these brain systems have some matrix structure also in the charge sector, and okay, it's probably just that. But these more recent works seem to find something stronger, so that's great, or something more general. Instead of delving into that, which is actually more challenging than what we will do, I'll first observe that happily in cosmology, we'll be in a multi-field context. We all know that the gradients dilute very rapidly, so being at zero spatial momentum or close to it is what we're generally dealing with. And in the multi-field context, the additional fields have these meaningful interactions outside the horizon. And indeed, as I just said, they're automatically at threshold. So this kinematics, which is a very special kind of unnatural thing in the collider physics context, is where it's at in inflationary cosmology. So this, this audience doesn't need this. This is like speaking to the choir, but in the HEP-TH world, there's a certain narrative that de Sitter is way too complicated to handle and so on, which is not, it's kind of a false narrative, and in some cases the situation is reversed, like here, the de Sitter expansion makes things easier, as we'll see. And there are other examples of that, including a proper rigorous proof of the stability of the Kerr black hole is known in de Sitter, Andres Vassi and his collaborator, but not otherwise. So de Sitter and this dilution effect can be a simplifying feature. Okay, so in this talk, we'll do some simple calculations to show that indeed then this enhancement persists. This will also lead to new forms of primordial non-Gaussianity with applications to PBH production and possibly other observables. The strongest version of this, where the tail of the primordial distribution will be heaviest, that in the explorations that we've done, is in the context of hyperbolic field space, which is a well-motivated starting point, in which case the tail is really quite heavy. But we'll build up to that through more prosaic models.
Sorry,
And
can I, Eva, sorry to interrupt. So I didn't quite, so what is it that, I understand that the gradients shut off in the sitter, so that helps you with the diagrammatics? Is that the, some in diagrams, or what is it that helps?
So we'll see. I'll just show you. This is stuff you're used to in a different language. I'm just connecting it to this particle physics version of the question where they were able to address it, perfectly easily at threshold, at low spatial momenta. At this point in the talk, I'm just observing that, well, we naturally work at low spatial momenta, so we might expect it to be easier to address, and that's what we find.
Okay.
The methods I'll get to. Yeah, I didn't mean to imply that it's now all obvious.
Okay.
Does that help? If there are any other questions, please keep going, because that's what it's about. Okay, so in its full glory, the statistics of the primordial perturbations are contained in some wave function that we don't know. It would generically be a mixed state with a probability that's given by tracing out all the other fields, which we'll call here chi, with zeta and gamma being the usual scalar and tensor fluctuations. We'll focus on the scalars. And we all know that this, is a very interesting quantity because it allows us to test certain aspects of the dynamics that pertain 14 billion years ago. But it's hard to do systematically. There's been, a beautiful development over the years, starting from proper calculations of the effect due to Juan and Paolo and company, realizations that if you have more than one field, or if you have general interactions, the shapes of these will vary and the strength will vary. This can be packaged in the low energy effective field theory to some extent, but still surprises keep coming from the top down, like we'll see one here that pertains to large endpoint functions involving heavier fields, heavier than Hubble, making a difference. And it's an ongoing enterprise to understand all the interesting dynamics that can contribute to this, that is both, conceptually interesting and also phenomenologically accessible. It's the more one thinks about this, at least for me, the harder it seems to do it fully systematically, but that's both a challenge and an opportunity as usual. Okay, so ideally we would just compute, and then we would evaluate the likelihood and compare theories that way. Instead, we've been working with proxies like the correlation functions that are being computed using increasingly elegant methods by a lot of the assembled people here. Another quantity, though, that can be used that's more relevant to this discussion of the full distribution is, say, a histogram of points in the map that one might compare to a theoretical expectation value for the number of excursions at a given value of zeta, although one then needs to compute the statistics of that and properly figure out how much one can learn from it. So, this is just a hard quantum field theory question, but it's good to keep the perspective, in my opinion. Of course, there's been a lot of work, beautiful work, constraining this in some key directions in this vast space. But like I was stressing before, it's hard to just do it, fully systematically. So, we need more. Here's a recent example that goes beyond low point correlators. It goes beyond masses of order or less than Hubble. So if you take a situation like we find in, say, axion monodromy, where whatever happens is repeated, one thing that can happen is if you have generic couplings not tuned to be very small, so not with special symmetry assumptions, then particle production events happen, or even stringy production events happen. And if they happen repeatedly. And in that context, as we found with Leonardo and Merdad and Raphael Flauger, this can lead to observable consequences in both the power spectrum, but also in the non-Gaussianity, and in this case, in a way where the higher point functions can be more important than the features in the power spectrum. After this, effect was theoretically derived, the effect being repeated particle production, and from that sourcing of scalar perturbations. Moritz and Kendrick Smith derived the optimal estimator for the part of the shape that we actually calculated in this project, and they analyzed it WMAP, not yet Planck. It's an example that brought up the theoretical possibility and quite reasonable possibility of effects that are best studied not at the lowest point correlation functions. And this is something that others have worked on as well in different ways. Enrico had interesting calculations of higher point functions earlier. Dick Bond and company have been very interested in this kind of thing for a long time. There are kind of statistical approaches that Dan and Amin and Mustafa pursued and so on. But this is a very sharp example where it illustrates a couple of things: the higher point functions being relevant and higher masses than Hubble being relevant if you don't choose to turn off couplings. Okay, so
sorry, just a question about the features that you found. So they change. If you should keep the shape of the polygon fixed and just scale up and down the size, and then I should see some modulation, or are there also features related to dialing, going to specific kinematical regimes?
Right. So, okay, I should stress this. The reason this was so calculable is that we computed a contribution to the shape, which factorizes. So it's basically in a sort of heuristic diagrammatics. It's like you have this particle production effect, and it sources outgoing Bremsstrahlung radiation, and the simplest contributions to that are just independent outgoers of that sort, and in that leads to this formula where we have this product structure. With this shape, the shape has the oscillatory features you're talking about. It's the same kind of features we saw earlier in axion monodromy with logarithmic variations. But I should stress, and actually I said it down here, but forgot to mention, this is one contribution to the shape. There are others, hybrid contributions, where more legs come out. In an axion theory, there are lots of interactions. So this isn't, there could well be stronger contributions in this theory, in particular ones that have to do with this factorial combinatoric stuff. So this, in fact, is what led me to worry about that. So if that's what you're asking, yes, there are different shapes that could also appear. As far as this shape goes, the kind of scale dependent thing that I think you're asking about is here.
Right, but maybe it's a related question. Do you think that this particular shape that you calculated is the dominant one in certain kinematics, or you have to dial couplings, or?
Yeah, we don't really need to establish that it's dominant in order to study it. We need to believe that it is orthogonal to other shapes which may be dominant. So in other words, searching for this shape is meaningful if it's not going to be canceled by some other contribution. And it's that we really considered here. I don't think we had any argument that it is in fact the dominant shape, and I was worrying that it wasn't for these reasons. In this context, there's factorials all over the place in the, not just the number of points, but the interactions as well. So yeah, so I just think it's, yeah. Thanks a lot for the questions. This is all on target. Okay, so let's think. I'm going to do the next. I'm just going to kind of hone in on this problem by first being general, thinking about generally what we might expect in some abstract way, and then going down to a very, very simple, essentially trivial example where we show this. So, but generalities first. Let's suppose we stack the deck for Gaussianity by starting with a product of Gaussian states for the inflaton fluctuations related to zeta most directly, and chi, this extra sector, and we start in a Gaussian state, the usual form, but then we decide to, since there are many time-dependent effects that can occur, let's mix the two sectors at some time. Let's not assume the couplings are particularly weak or any of that, and make a sudden approximation, just like in ordinary quantum mechanics. So then the wave function from that point evolves in this standard way, where these ions are the eigenfunctions of the mixed Hamiltonian. And, you know, if you just write down the formula for the corresponding density matrix, you know, it really has no reason to be special, to be unmixed. And, you know, for all we know, that could generically have a very strong tail of the distribution. This is very abstract. This doesn't really establish anything, but it seems to me reasonable to expect that. Instead of pursuing that generality, what I will do, as I said, is to go to a really trivial calculable class of models and just see what happens. So let's have our chi sector be a two derivative action with a kinetic and potential term. Again, we introduce some mixing interaction, and let's take one of this form. This is a standard type of interaction that it can come from a curved field space, which is of interest to many of you for various reasons. And in this context, our interaction over some time window will be of this form, where then we can, you know, expand it around the background, and it leads to a coupling between delta phi dot, or really the field momentum for delta phi, and chi through some function f of chi. So in the hyperbolic field space that I alluded to before, this would be exponential. Play with some things that interpolate between some power law to that exponential. So here's our mixing interaction again in the Hamiltonian formalism. It's that delta phi dot translates into a field momentum, and this mixing part dominates over the free part during this time window, which leads us to be able to obtain the wave function upon time evolving by this small time delta t, let's say, as a very nice simple action of a you know, e to the I pk sort of thing, so a shift in field space. And the wave function then is immediately calculable to take this form where delta phi is shifted by the coefficient of the field momentum that appears in the mixing Hamiltonian. And that leads to a formula for the likelihood that's a convolution with some coupling that depends on the background evolution that we keep track of. Okay, so this form will enable us to quickly see what happens to, if you like, the correlators, the high point correlators, and you know, the behavior of the tail of the distribution. So in general terms, you know, in this already simplified context, the non-Gaussianity can come from one or both of the mixing interaction and the potential. One thing we'll stress is that it arises even for a purely Gaussian chi sector, with the mixing being the thing that injects the non-Gaussianity. The chi sector itself may be highly nonlinear. One has to be careful about applying that at different scales, but we'll also study that. Okay, so what's the basic idea? The basic idea is the following. We start from this formula that I keep flashing, where we got this convolved probability distribution, and where the tail of the distribution would have been Gaussian from this factor. We now see, as we do this path integral, that there could be, that the chi contributions to this path integral could cancel out that that very strong Gaussian suppression of delta in terms of just the usual Gaussian function of delta phi by coming along and, you know, canceling against the delta phi for large delta phi excursions. Okay, so if you look at a configuration like that could arise as a saddle point contribution, for example, then you would estimate that the probability at large delta phi is then given by, you know, evaluating this factor at that value of chi saddle that, you know, in turn depends on delta phi, and, you know, that effect can lead to a probability on the tail, say at large delta phi again, that is much larger, much heavier as a tail than the Gaussian wave function.
Sorry, can you quickly explain again what is a psi orthogonal?
Right. So we had two sectors, chi and phi. And we can consider, oops, we can consider, you know, a nonlinear chi sector, and that's where I'm allowing for this general psi perp. Perp just for me means orthogonal to the inflaton. And so here we're just leaving this general. As I said before, if we just keep this Gaussian, we'll still get an effect from this mixing. But what I mean by this psi perp is whatever the wave functional is for the chi sector before
Okay.
yeah, before we mix. Okay, so let's get to the formal question first. So for that, we can calculate the generators of connected and disconnected correlation functions by integrating against a source. So W of J is the generator of connected correlation functions. And so let's just plug in our probability here, which has a psi perp squared factor and also the Gaussian with a shifted argument. And now you notice that we can very easily do the delta phi integral that goes into the calculation of W of J or Z of J, because it's Gaussian no matter what we have in the chi sector, no matter what this mixing interaction is. So let's do that. And then we get this expression for e to the minus W of J, you know, which is some path integral over chi still, that, as we just discussed, depends on the dynamics of chi. And we want to, for this formal question, we want to understand whether or not the factorial enhancement obtained by taking n derivatives of W with respect to J that gives us the correlators, whether that leads to a factorial enhancement. Okay, so as you might imagine, that's now calculable. Let's say, for example, do even a very simple mixing interaction, which is just quadratic plus linear and Gaussian psi perp. And there, you know, everybody's Gaussian. We can just do everything, and we get some expression for W of J, where which we can then differentiate and find explicitly that it sustains the factorial enhancement. Here there's, you know, a tree level contribution and a one loop contribution. Okay, from the determinant. Okay, so that's clear in this completely trivially calculable example of the full field theory. Now, if we want to study this further in more complicated situations, it's useful to simplify the calculation that we're going to do for this formal question and focus on the 1-point PDF. If we allow for non-trivial interactions in the chi sector that are governed by the stochastic evolution in the chi sector, then we can use the Starobinsky-Yokoyama results, for example, to calculate the equilibrium distribution for the 1-point PDF in the chi sector, which this has been reviewed in various of the interesting talks in this workshop, for example, and probably everybody is aware of this. It goes like this, and it's a very nonlinear, non-Gaussian thing in itself. And one can calculate various quantities associated with this, like 2-point correlator and well beyond that. So one can compute all sorts of quantities in this equilibrium distribution. One has to, you know, so one massages the formulas into well, one of the relevant calculations in this process is this one, which determines the what I've called these lambda n's. The first one of which appears here. These are eigenfunctions of this operator on the left-hand side, which depend on the shape of the potential and which govern what the correlation length is beyond which this whole description applies, and also relatedly the time scales after which it applies. Okay, so anyway, this is a way of getting a handle on some of the nonlinearities in the problem. And for a formal analysis, this is fine. For phenomenological applications, one has to be very careful about the scales of, you know, this doesn't just immediately introduce some signature. But for the formal question, let's focus on this first. And then we have an explicit expression for this psi perp that is given by that Starbinsky-Yokoyama result. And that has been derived recently by Victor and Leonardo, and others have worked on that too. And you know, as I just said, it's, as we'll discuss further, it's a little subtle to apply that directly to observations. Okay, so the thing we'll use for this is just the histogram, and therefore study this factorial enhancement question, the formal question, at the level of 1-point functions. I mean, sorry, at the level of not 1-point functions, but correlation functions at a single point. And then this path integral becomes just a simple integral at that point. And we want to understand first whether or not the factorial enhancement persists. So that's what I keep calling the formal question. Okay, so let's do that. So for both z of j and w of j, we can expand those in power series in j. There are some coefficients. Let's call them zn and wn. And you know, in order to avoid the factorial enhancement, we need these zn's or wn's to die like a factorial, to cancel out what would be the factorial enhancement, just in this formal expression. And basically the point is that can happen, yes, but very rarely. That happens if the function is entire, which is very rare. So, you know, for example, we could have this f of chi grow more strongly in some direction in the complex space than v, and then this will diverge, and there's no then the factorial enhancement is not removed. If we do the connected correlators, for example, we can show this explicitly from this structure in this class of models by looking at the saddle point equations. So for those, we find saddle point, which will be a solution of the variation of this exponent vanishing. Combining that with the fact that w of j is then the value of that exponent at the saddle, we can conclude that dw dj is nothing but this f evaluated at the saddle, this mixing function f evaluated at the saddle. That in itself will have an expansion in the sources j, and so w has such an expansion, and we basically want to know if these an's kill the factorial enhancement or don't they. So okay, let's simplify to a really particular value of this f, and in that context, we see from here that then j would just be v prime, and so df dj, which has some expansion whose coefficients again we want to understand, is then just d psi star dj, or 1 over dj d psi star, and so you know, if j prime is 0 anywhere, then which here means like v double prime being 0 anywhere, then the function is not entire. Okay, so long story short, it's very easy to show that the expansion, the factorial persists in this problem by showing that w of j or z of j is not entire. One can do it also where w of j, or one of them is and one of them isn't, but maybe I won't belabor that. But for example, if z of j has a 0 anywhere, then w of j is not entire because it then has a branch cut by taking the log. Okay, so let's come back to the interesting physics of this, which is the estimates of the tail of the distribution more specifically. So let's say we work with an f of chi that, say, interpolates from one of these low powers of chi all the way up to the exponential, in a sequence where just for formal reasons we let go from m equals 2, say, up to infinity, infinity being the hyperbolic. Okay, so and let's say we work with one of these well-motivated potentials from top down. Doesn't really make any difference, but chi to the p sort of potential. Okay, so then we can carry out the thing I said in words before, where we see how this F mixing cancels out what would be the suppression of on the Gaussian tail. In this case, by chi to the m being up to these factors of the coupling, being delta phi. Okay, so that's here, and then the remain. So that just cancels. This then becomes 1. This factor, and we evaluate this one, and we get from, say, the Starbinsky distribution, we have then the thing in the exponent is chi to the p, which is then delta phi to the p over m, which is much heavier than Gaussian as we take m bigger and bigger. And again, this would not be terribly well motivated, aside from very formal reasons, except for the fact that it does extrapolate to a quite standard shape of this interaction, where indeed this becomes a log. So in this class of models, the tail becomes heavier as m becomes larger, and it extrapolates to this super heavy form where it's the exponential of minus a log squared. Okay, so the tail can easily be heavier than the Gaussian for this kind of reason, and still, if one wants to be practical about this, we have to ask, okay, at what probability does the this tail, what overall probability does this heavy tail start to exceed the Gaussian? The whole thing is normalized, so it has to be some shape like this. And this is of practical interest if we have enough data to probe that. So roughly, is this bigger than the 1 over square root of n? And that's a model-dependent question. So you can check for various values of p or m in the sequence, what the answer to that is, and in particular, what the best, where the most information content is in terms of which endpoint function. So, if you look at our paper, you can see, some playing around with that, with clear examples where the endpoint function can be best, can contain the most information, beyond the low point correlation functions. Even taking into account the fact that the overall tail is suppressed in probability. Okay. Now, when it comes to the scales, one has to be careful. So I stressed before that it's the mixing interaction by itself can introduce the non-Gaussianity, in which case this whole discussion of the stochastic inflation and so on is not relevant. But that discussion is very interesting. For all the reasons people have said over the years. And when it comes to that part of the non-Gaussianity, we need to be careful about when it applies and what conditions there are in the parameters for that to be relevant. So here what I've drawn is various very basic scales in the universe. There's the size R obs of the observable universe, which of course is just Hubble amplified by the number of E foldings, E to the E and E. There's this Starbinsky-Yokoyama correlation length, which depends on the dynamics through this eigenvalue lambda 1 that I mentioned earlier. So that's in green. And then there's the resolution of the survey that you're doing. And so let's insist minimally that the scales are arranged in the inequality that I've depicted here, where the resolution is fine enough and the correlation length is small enough to have that the whole discussion of this equilibrium distribution apply within an observable patch. Okay, so that's this inequality here, which we can translate into this inequality. Now you have to know that this lambda 1 is, you know, some simple function of the couplings of the theory. Depends on exactly what theory, what formula this is, but clearly within this CMB where there's limited resolution, this requires some fine tuning to get the couplings into this range where it matters for the CMB. But that's part of why we then applied this first to PBH production, where this is not a constraint. Now there's something else which is quite interesting about it, though, which was stressed in this paper. We had a talk by Spiros about it, where the stochastic stuff actually becomes potentially more interesting if instead of the sort of potential that I drew, where it just drifted inward, one has, you know, more generic shape where you could have a field excursion that then evolves to larger and larger field excursions because the potential forces it to drift outward from the boring Gaussian region. So that, you know, would enhance all these effects that I just discussed. However, one has to be careful there to calculate the this lambda 1 that I mentioned in order to check what happens with this in this more elaborate potential energy. Okay, so that's a detail, but I think it's an important one for this direction, and there's progress. Okay, so as I said, one can apply this to PBH production rather naturally. Again, to get a handle on things, at first we go to a large flavor expansion with a more boring version of the interaction, and we can calculate everything very explicitly there, and we get a large PBH abundance. Let me not dwell in details because the time is short, but it's hopefully now intuitively clear why that should be. PBHs have are large excursions in field space that are localized and large, and that has to do always with the tail of the distribution. So this mechanism doesn't involve building in some huge spike in perturbations at the Gaussian level. Instead, it has to do with the actual heaviness of the tail of the distribution. There's still a lot of theoretical space for when this happens, and therefore what scale of black holes one has. And there are conditions that one is very careful about, having to do with making sure that the CMB low point correlators aren't adversely affected by this in a non-viable way. So we check that. You can see all the details of that in the papers. Okay, and this NF is in this page is a for theoretical simplicity, a large number that we put in. This also helps us with radiative stability, because one loop dominates in the calculations. But this hyperbolic field space that I keep alluding to gives it this super heavy tail with just one flavor, and it's also radiatively stable, as Adam Brown and I think Dan Green also showed in some earlier work. So which makes sense. It's kind of based on symmetries of the target space. So in that case, there's no need for such a parameter. Okay, so I won't necessarily.
Sorry, quick question. You mentioned that you're trying to keep the 2-point function under control, but will it make some prediction for the 3-point function, saying the CMB?
Well, right. So I'm glad you asked. It's a great question. The thing we're really working with here are these types of distributions where, you know, the best endpoint function is really some higher point function. So it's not a strong effect for low point correlators in the first case. Now, I guess you're saying, given that we needed to be careful about the 2-point function, don't we need to be careful about higher point functions? Yeah, maybe I could think again about that. It's been a while, but
you say that you should look for higher point functions, but do you have do you expect them, for example, to be scale covariants like the 2-point function is, to inherit at least something? Maybe it doesn't have all the Sitter symmetries and so on, but there is something that we know and love that these higher point functions will have.
So, sorry, could you say a little more what you mean by something we know and love?
I like, say,
so,
scale covariance. They will go like 1 over k to a certain power, where the power is fixed by scale symmetry.
Right. Yeah, I don't think we've done anything here that changes that. This, like that, yeah, the interactions here aren't changing that. There, what the dependence on the fields is
Okay.
on the tail.
Yeah, that was my question. Okay.
Can I have a question?
Please.
Hi. I have a question about the background evolution. So the condition that you have to cancel the Gaussian tail, if I translate it into the background evolution, does it mean the field chi has to be rolling at the same time the inflaton is rolling instead of sitting at the bottom of potential?
No, not really. I mean, you know, phi dot can be very, very almost constant, right? So what happened?
Phi dot constant. Yeah.
Yeah. So what happened is.
What about chi dot? Chi is the second field, right? It's
yeah. But the way, right? But this is canceling the perturbation. It's not canceling the. In other words, the kappa. I think you're asking about the kappa. Yeah. This kappa is basically phi dot. I'm sorry, I'm trying to go back all the way to the formulas of that. But yeah, so kappa itself is phi dot. That's not changing. What this is canceling is the perturbation in phi, not the background phi. Okay, so you got to be very careful with that. I should stress that.
Right. So so if the field, for example, is sitting at the bottom of some potential, will I expect it has some Gaussian tails nonetheless?
Well, the point here is that the greatest probability, given this result for the probability, the greatest probability is for chi to be not sitting at some random place, but instead to be, you know, doing this, to be being in a configuration where it cancels this tail. So there's some excursion in chi. In other words, there's some excursion in chi that's governed by this part of the wave function. Yeah. Okay. Now I think I'm getting what you're asking.
Yeah.
Right. So indeed, I should go back to the slide where this is exactly said. So we look at the biggest contributions to this path integral, which for large delta phi or equivalently large zeta are where this f mix cancels this. And then, as you're saying, I think the penalty we pay in probability is then governed by this psi perp. Okay, so if psi perp can be just Gaussian, if this mixing is, say, this hyperbolic exponential, then, you know, this could just be Gaussian, and yet the suppression is not the standard Gaussian anymore because as a function of delta phi. Okay, so it's a Gaussian as a function of chi, but not as a function of delta phi. That's exactly the point. So let's go to the picture. Yeah, that you know, that's the point. You get some funny formula here in this formal series of examples. But yeah, does that answer your question?
Yes, thank you.
Thank you. Good to see you. Okay. All right. Yeah, I was told to make this 50 minutes. Let me just therefore flash through the rest, and we can discuss more as you wish. Okay, so maybe you can believe me that large NF gives us radiative stability because one loop dominates as usual, and that was part of our analysis. That, just for fun, I want to explain this thing that will come out very soon in a paper, which is that okay, if you do this large NF loop calculation, where we have this coupling between phi dot and chi, let's say in the case now again where chi is quadratic, we can integrate out chi, let's say with many chi's, and that gives us a Coleman-Weinberg-like expression. So, you know, the role of the usual V double prime in such a Coleman-Weinberg expansion is now played by this phi dot squared, okay? So there's a very good approximation, this one loop dominance approximation at large flavor number, where the effective action has this logarithmic branch cut. And, you know, we have a choice of what sign here to put in. And I put in the appropriate sign for what I'm talking about now. That branch cut forces a speed limit on phi dot, okay? So before we had the branch cut of a square root sort in the DBI case, and from this effect, which was associated with large color from ADS-CFT considerations, and now at large flavor, we find a logarithmic branch cut with again, a speed limit. Okay, so I find this quite amusing, and with a few students, George, Deshawn, and Alex, we've analyzed this, and we'll put out a paper that's, you know, quite ready. But as before, you can work out, you know, first the non-gravitational case, and energy conservation immediately shows you that indeed there is a speed limit, that you don't go beyond the branch cut in velocity space. And so all the same effects occur here, inflation on a steep potential and so on. There's some nice formulas using the Hamilton-Jacobi formula system for you know, the evolution. And so here there was some scale m star in the problem of this higher dimension operator. And since that scale is divorced from the Planck scale, all the dynamics depends on it and not m Planck. And so for that reason, and quite explicitly, one finds that the condition for inflation, you know, is slow variations on the scale of m star, not m Planck. So if m star is much smaller than m Planck, then, you know, it's a more general version of inflation with the same sort of predictions and constraints that we have for the other case. Okay, so I mentioned that her name is Zeta, and the summary of this talk is basically that, you know, sometimes you can see her tail, sometimes you can't. The real summary is here, and I'll stop and wait for any more questions.
Can I ask some question?
Please.
I was wondering that this factorial enhancement is a generic feature. It seems like whenever you go to the tail of the distribution, and it seems to me like it depends on the interaction, the mixing between phi and chi, and the form of the f of chi. Is it true?
You mean how much does it depend on that? Well, yeah, I'm saying it's generic in the sense that, yeah, coming back to these forms, you know, these things need to be entire functions for this not to happen, and that is not generic. So you could cook something up where it's true, but I think it's fair to say it's not generic. It's true that it is generic for the factorial to survive. And I tried to motivate that it's, you know, not surprising that from the point of view of the original investigations in field theory, where people established this at low momentum, and here we're at low momentum, so it's more or less that effect, I think. But yeah, in terms of the genericity argument, it's, you know, only if you kill this factorial by having these coefficients die, meaning it's an entire function of J, that you would avoid this conclusion.
I have a quick question. Can we see this enhancement in the coefficient of the wave function?
Okay, so can we see this enhancement in the
coefficient of the wave function? Like if we compute the coefficient of the wave function?
Well, I mean, you know, what this is formally is you know, a path integral psi squared delta phi to the n, right? So the wave function psi enters. I don't think it's particularly useful to, you know, do an expansion in this context, just because we're talking about ultimately the tail of the distribution. But maybe for any finite n, there's some. I would have to think about it. I'm not sure if you can boil it down to something like that. But here I want to stress that the calculations are really quite humane. I mean, they're not difficult. It's not difficult to see what I've shown you. If anything was unclear, please ask now or later. But I'm not sure if you could see it in that kind of expansion, and I don't see why you need to approach it that way for the reason I'm talking about here. That this again, these calculations I'm doing are easy. So does that help?
Yeah.
Okay. Oops, I don't know why I keep flipping around, but are there any other questions?
I have a question.
Yes.
It's kind of two questions, but I wanted to be sure that I understand. So basically, you are solving the Schrödinger equation for the conversion of chi perturbations into phi perturbation. That was how when you exponentiate that conjugate.
Right.
I didn't fully understand. Is that is an approximate solution in perturbation theory? How should I think of that solution? Where it's exact because you have chosen a careful interaction?
Happily, it doesn't depend at all on the interaction, and it is non-perturbative in what I call kappa here, or this coefficient. The approximation comes in saying that it's just this simple shift in field space depends on this mixing term being the dominant part of the evolution over this time period. Okay, so there's already some correction from this, and also we didn't integrate this. I think in Spiros's talk, he wrote a more general form for this, a somewhat more general form for this. But here we just did the dumbest thing of making this delta t small enough that we could literally write it like this. So there's an approximation there involving a small delta t. We were careful about that. You can see in the paper how that fits with all the parameters. But again, we're doing this not to be totally general, but to just make the point that this easily happens. So yeah, but it's not what I want to stress. I'm sorry, is it's non-perturbative in this, and it leads to non-perturbative results in delta phi.
Do I think of that delta t to be like a very short, like one e-folding, or to be like the whole?
For simplicity, think of it like that. Otherwise, one would have a more, since there are time dependencies in the problem, one would have an integral expression.
I see. Because related to that, I was wondering if you expect the predictions to be IR regular or IR singular. Some interactions might give you some IR singularities, but because you don't integrate this, maybe you don't see what happens after long periods of time. Is there some argument that?
Well, here I'm not sure I was very clear about this. Here we just say, because things are time dependent, and now I'm saying in terms of the background, let's consider a situation where this interaction pertains over a finite time. Okay, so this delta t is small. I think maybe you're saying something about it nonetheless having long range effects later in time, even though it itself has turned off. Is that what you're asking?
I mean, if you turn it on and off, then you would expect the result to be not scale invariant, to have like some features. While if you keep it on all the time to ensure scale invariance, then it wasn't sure to me that you don't get some log enhancement over a long period of time for some reason. It's not obvious because I haven't thought about the problem in detail.
Oh yeah, I'm sorry. Yes, yeah. Now I realize the previous question might have been about that. Indeed, and here we ultimately pick a time where this is happening, either reheating, which is kind of a standard thing, time in which one might consider all sorts of non-trivial interactions to come in and out of existence, or some other time. And as you say, that introduces scale dependence. I think we had asked that earlier, and I maybe answered him incorrectly, because that what you're saying is true, and that is though of interest for applications like, say, these PBHs where you do the mixing, then dictates, okay, what scale is it that you have the excursion and you have the massive black hole that corresponds to that. So yeah, I'm sorry. I think I confused the discussion earlier when this was asked, but as you say, with this finite window, there's a choice there of scale on which things are happening.
And related to that, do you at the end only basically compute the real part of psi, or like the psi squared, or you actually compute all the phases in this approximation of the wave function?
Yeah, the phases aren't playing a role. The probability is what's playing a role here. I understand you have interesting formal developments or beyond formal, I don't know, on the phase structure. Just coming back to the general type of question you're asking, I mean, I do like thinking about it this way. I mean, just in general, we would expect large entanglements to build up, and hence probably, this kind of effect where chi can cancel the Gaussian suppression on the tail could be, quite a bit more generic. So I think thinking about it in general is a good idea. Maybe you can tell me what role in observables, or, let's say observables connected to the tail of the distribution that do matter, that do depend on the phases, because, what I computed was more the probabilities, but
exactly. I understood that was your interest, but because of the approximation you made, it seemed to me that maybe you could have kept track of the phase just as well. It's just that you didn't care about, and that was the case. That's maybe something interesting, because we would have some non-perturbative understanding of what happens to the tails in this class of models, and maybe there is something non-standard to learn from there. I was just wondering if I can do the same calculation by keeping all the phases throughout.
Oh, that's a nice question. Yeah, on the face of, well, okay, I'll have to think about it. Some of these manipulations involved these squares, but I mean, yeah, I could think about that. Certainly this part that you were asking about was at the level of the wave function. So and then the question of, so yeah, so the wave function being the square root of this, if you want, with appropriate phases, would still be true. It'd be this convolved form, and instead of computing this likelihood, you would just work with this wave function. Yeah, I mean, I don't see why that much isn't true. What would you do with it? Like what?
It corresponds to, for example, instead of the delta phi to the n, it would be like delta phi to the n, pi to the m, where pi is the momentum conjugate. That type of, it's a single point correlator, but you look at the PDF in that direction, and okay, well, it might have some, maybe it's a theoretical type of information, but it could be interesting.
I see. Yeah, that is interesting.
1 point.
Yeah. Okay. So, I mean, usually these phases have to do with interference effects in quantum mechanics or something. And do you have a picture of how that enters in this kind of cosmological context?
Yeah, no, not very well. I mean, yeah, not very well at the moment.
Okay.
I can chat with you more about some.
Sure. Yeah. Yeah, that sounds interesting though. Anyway.
Eva, can I ask a question?
Sure.
In this scenario where the primordial black holes come from the heavy tail, as you explained, do you have some statements about the clustering of these primordial black holes?
I don't. You can tell me more. I mean, I understand that that's a question, and it gets very detailed. Yeah, I don't have anything to add about it, but maybe you can make some comments about the issue.
Well, I'm just trying to make guesses here. One important thing to know is we know there's always a contribution to the power spectrum of these rare objects, which is just coming from just Poisson noise, 1 over the average number density. That contribution is always there. And if you have these objects actually coming from the tail, the question is whether there are situations where the clustering from that, because of that, actually is above the Poisson noise, the 1 over number density. If that is true, I think that could be interesting. I do not know. I don't have a good sense whether that might happen.
Well, that's okay. Now I think I'm with you. You're saying given that this is a rare event, so to speak, what the rareness of clustering or the distribution of clusters is another calculable thing that could, how close they are to each other generically in this distribution. That's a very interesting question. I don't know the answer.
Right. Your calculation, which basically address the average abundance, so that already tells you what is the Poisson noise. But presumably in your model, there is a prediction for, let's say, the 2-point function of these rare objects. And the question is whether that might actually, in some cases, exceed the Poisson noise contribution.
Yeah, no, that's a great question. I'm sorry, I appreciate the question. I just don't know the answer. Thanks a lot. That's a good idea. What has been calculated on before? Can you summarize the status of this? And
I have to confess, I don't know.
oh, okay, you do. Okay.
Probably hear that people here that might actually know more than I do.
Wouldn't you need some squeezed non-Gaussianity to have non-trivial clustering?
So could you elaborate, Merdad? I mean, so correlations on long and short scales are necessary in some, is that what you're getting at?
Yeah, I'm just guessing if I want to have a non-trivial effect on clustering, probably I need to enhance the squeeze limit, which I didn't expect to get in these models. But that would be my first guess, but I haven't thought much about.
Okay, and again, can you just slow it down for me? The intuition is clustering involves things, being closer to each other, so there's some correlation. But you're saying there's some correlation between large and small scales that required. I'm just being slow. What? Can you just state the intuition a little more slowly? For the connection to local non-Gaussianity.
Yeah, I think what Merdad has in mind is probably something like this. Where locally you actually form a primordial black holes has to do with basically high fluctuations locally, whereas the question of clustering between black holes has to do with, in some sense, a larger scale correlation between these objects that form from basically local high K fluctuations. So it involves basically.
I see. Okay. You're saying the cluster itself is not. Yeah, you're saying the cluster size itself is the larger scale.
Exactly. I assume that's what Merdad is.
Okay,
yeah,
thanks.
that was the thinking. I don't have any precise argument.
But if it were equilateral, then all the scales would be sort of the same, and you'd have a cluster of really well grouped objects by that logic. Perhaps I don't know.
Can I just make a comment here?
Yeah, actually, before we do that, maybe we can just kind of thank Eva again and move on to the discussion part. So if people want to.
Thank you.
Thank you for the discussion, everyone.
Related to the clustering thing, I think the discussion is parallel with the non-Gaussian correction to the bias when you have the multiplier spectrum, right? And is indeed because you couple, if you have a local non-Gaussianity, you couple long and short scales. So you expect when there is a peak of a long mode, the short modes will fill this peak and they will go above the threshold, so there will be a localized clustering of black holes in this case. So I think in this direction, it is interesting because also in this kind of discussion where you have like extra fields around, I think you expect in general local non-Gaussianity to appear. So it could be indeed relevant for clustering primordial black holes. I mean, related to these questions.
Okay, well, this is really interesting to me. I would have to think about it and calculate a bit more to be sure, but yeah, the question is very interesting. So then this affects what the actual ultimate masses are, because if they cluster, is the idea then they're going to merge, and that changes the mass, or it changes something about.
It changes a lot of things, and also it changes a lot the constraints on the mass distribution and stuff like that. So it also mergers, you know, maybe gravitational wave related question. I think there is an interest in clustering. So.
I see. I mean, for me, what fascinates me in general in the subject, of course, is the overlap between the, you know, formal conceptual field theory and beyond, and some observable. So here it has to do with the, you know, the behavior of quantum field theory at large excursions. You know, I think Merdad put it when we were talking earlier about, you know, resurgence. There's this resurgence idea about, you know, and so resurgence of PBHs. I don't know. I just, yeah, I feel like there's a lot more to exploit here, but it, as usual, it's really hard to do things.
There's also some very interesting stuff here, because, I mean, you're talking about heavily, you know, deformed Gaussians deep in detail, and I think then, like, the perturbation theory that we know in QFT and we use all the time kind of loses meaning, right? There's no point in talking about Feynman diagrams in the usual way when you are computing these high endpoint correlation functions, because exactly you are not at all close to a series expansion around the Gaussian. So, but still you can define correlators, I mean, and compute them. Like in this case, you compute histogram correlators. They're really easy and very well defined, but still I think the diagrammatic interpretation that we use all the time in QFT, I think it's getting a bit obscure in this picture. I don't know if you agree.
Well, no, that's true, but happily semi-classical methods can be effective, and that's the kind of thing that we, you know, that we transition to. But yeah, and the other thing I want to stress is there's a lot of elegant calculations going on, and I think it's very beautiful, but it has to be kept in mind that, you know, a lot of those kind of sacrifice genericity of interactions, make very strong symmetry assumptions or whatever. And so, you know, if we really are serious about doing this subject systematically, we have to get, you know, keep a perspective that includes a much bigger picture. And anyway, in this, yeah, so I'm saying a couple of things at once, but that includes both, you know, situations that are less symmetric but more generic in any point correlators, and then also, you know, what is going on in the rest of the distribution. Yeah.
Okay, great. Yeah, I'm sorry to interrupt, but we have like a lot of things that we're supposed to discuss in this session. So maybe now is a good time. We've kind of seamlessly blended into sort of Spiros' talk, and there was some discussion in the Slack channel. Maybe Spiros wants to say a couple of words about what his talk was about, to maybe try to address some of these questions really quickly.
Sorry, may I ask one last question to the previous talk?
Yeah, sure, if it's not very long.
Yeah, since here you're also looking at hyperbolic field spaces, I'm wondering if you can see something for the spherical case as well, if the heavy two would be different.
That is not that, well, that doesn't have the exponential behavior, so I would guess no. That, I mean, that is, you could compute it, but I would guess it wouldn't be as strong of an effect. Happily for, you know, I mean, happily when it comes to geometry, you know, hyperbolic is by far the most generic situation. I mean, we could talk more about that, but it's, you know, there's, you know, infinitely many topologies that are possible with hyperbolic, or, you know,
Right.
dominantly negatively curved spaces, and so it's not surprising that that's what we often find, say, from the top down. So
Yeah,
So I think, so yeah, but short answer, I would guess it's not as strong an effect for a spherical, for positively curved target space geometry, for the reason that, you know, this exponential effect wouldn't be there. But thanks.
Yeah, thank you.